So it's a pleasure to introduce Jaume de Dios, who will talk about recent progress on the hotspots conjecture. So thank you very much for accepting the talk.
Well, thank you very much for inviting me to the program. I've only been here for a couple of days, but it's been really nice. And today, yes, I'm going to talk about the hotspots conjecture, but I'm also going to give a little bit of motivation about how I've been thinking about this problem over the past years, because I think the ideas generalize to other problems. And oh, the idea is as follows. So we have a Laplace operator, and we can use the same operator, the same Laplacian, to think of a lot of different physically inspired phenomena. One could think of it as like a generator for the wave equation, and that's useful sometimes. One could try to look only at the fundamental modes, and then you get an eigenvalue problem, or at the heat equation, or at some sort of energy, like elastic energy minimization problem, or through the generator of some sort of Brownian motion. There's sort of these little shadows on physical phenomena. That all in very idealized situations go down to being the exact same operator, which is the Laplacian. However, behind all of them, there's a more generalized version where you have a bunch of extra coefficients that would be related to the density of your material, the diffusivity of your Brownian motion, whether your little particles are feeling a force, the thermal conductivity, and so on. And as mathematicians very often, we want to go to the simplest, nicest to study situation, everything constant coefficient and so on. And the question is what can I get by studying only the Laplacian? Can I turn my back to all of these variable coefficient PD and sort of through the hotspot conjecture and other conjectures, what I want to argue today is that you cannot. That one should always try to have in mind which is the right variable coefficient generalization of the problem at hand. And that in order to make informed conjectures and so on, you're going to be making a lot more reasonable statements if you don't think only about the Laplace operator, but you keep track of which is the right physical interpretation behind all of the time. Well, physical interpretation or mathematical, but try to build the natural variable coefficient generalization of whichever system you have in mind. And I'm going to start with a very classical result, just to set the ground on what kind of questions would this apply to, which is Payne's conjecture. So what does Payne's conjecture tell us? Well, as always, I have any sort of wave situation. I can express it as a linear combination of fundamental modes. And we have a bunch of theorems that tell us cute things about that there have to be nodal lines. The spectrum has to split. Yeah, eigenfunctions have to split into certain areas where they're positive, where they're negative. And I have certain control in the ways it will have to break. And Payne was somehow trying to be a little bit braver. And he observed the following. When I look at the second eigenfunction for a bunch of different domains, there's a common pattern that eventually breaks, which is that the nodal line, which has to split the domain for the second one into exactly two pieces, will always do so by going through the boundary. So it's not going to be in the situation that we see for the fourth Dirichlet eigenfunction of the ball, but it's always going to be in this sort of situation where it's breaking the domain into two pieces by going through the boundary. And this is what Payne conjectured in the 80s. That for any reasonable, let's say, planar domain, you will have this phenomenon. You can, of course, there's natural generalizations to RD for surfaces. You can be as brave or as non-brave when posing the conjecture. You can talk about convex sets. You can talk about any set, and so on. And one of the brave generalizations that one could do to the conjecture, which one may think is too brave, but I want to claim is the right one, is a Schrodinger operator version. So the original Payne conjecture tells me that the first Dirichlet eigenfunction will have a zero set, a nodal line that will go to the boundary. One could even go up and try to say, well, I have a smooth function, so as a smooth set and maybe a smooth potential, and the first eigenfunction of the Schrödinger operator with that potential always has the nodal line touching the boundary. This, well, feels a bit stronger. It turns out that these two conjectures are equivalent. One direction is easy, which is, you can go back by just setting the potential to 0. The amazing thing is that you can go back. That if you manage to prove Pain's conjecture for free in a black box manner, you get it for Schrödinger operators as well. One way to see that is by doing microscopic perforations in your domain. It turns out that if you have a circle and you put microscopic perforations in it, you can use those perforations to essentially simulate any Schrödinger operator with positive potential that you wanted. Morally, what you're doing is you're putting an amount of perforations that's proportional to how big you want your effective sort of homogenized potential to be. What this tells you is that if you do it naively, which is going to be enough for us today, having no perforations is equivalent to having 0 potential. So the equivalence that we can prove today that's relatively, it's useful enough, is that Pain's conjecture is equivalent to a Schrödinger version of Pain's conjecture, where you ask that the nodal line doesn't touch the boundary, but you also ask that the nodal line doesn't touch the regions where the potential is positive. Why are those equivalent? Well, I can simulate any potential, as we're going to see in a second, by performing like microscopic surgery in my domain. And then if the nodal line doesn't touch the area where the potential is positive, it's not going to be touching the boundary, because the boundary is the union of the actual boundary plus the areas where I've made microscopic perforations, which are the areas where the potential is positive. Now, where does this microscopic perforation story come from? It's very classical. It's from Cianorescu and Murat in the 80s. So what they show is that if you pick a nice omega, by nice I just mean nice enough that like reasonable C alpha boundary regularity theory applies, and you pick a continuous potential, you can define a set which is the set of points that are slightly far from, I get omega, I get my original set, I remove a tiny lattice, but I not only remove a lattice of size delta, I remove tiny balls around this size delta. And I get this set omega delta, and then it turns out that the Laplace operator in this omega delta, which you should imagine as something like this. Now, since it's not exactly like before, it's a grid, and the size of the holes that I'm making in the grid is proportional to how big of a potential I'm trying to simulate. Now, what you can show is that in this situation, the Laplace operator on these domains omega delta with Dirichlet boundary conditions converges in resolvent sense, in the sense of like eigenfunctions, eigenvalues, and so on, to the Schrödinger operator with the potential that you used to build this. And now, once you have something like this, basically you've already won. Let me though try to give a little bit of intuition why this theorem is true. So what's happening in practice when you zoom in to a certain area of your eigenfunction is that, or your solution or whatever, is that it looks like the effective solution of the Schrödinger operator plus all of these tiny spikes. If we think of a Schrödinger operator, it has a usual Laplacian part, and it has, which would come from, say, a kinetic energy term, a Dirichlet energy term, and it has a potential part. Now, what's happening is that each of these spikes, if I have like my bulk value and I have to go down, I have to spend a certain amount of Dirichlet energy to go down, which is proportional, well, to how big I am. So in the end, when I look at the energy of this effective system, I will get the usual like large-scale Dirichlet variation plus the sum of all of these microscopic contributions, which are as big, which are proportional to the size of the function. So I'm going to get something that's just multiplying the size of the function, which is the potential. And then the size of the spikes You fine tune it, you solve it carefully to get how do you call it? To get the right amount of energy. Now, this convergence, as you may assume, is not convergence in L infinity. It's convergence in L2. For example, if I want to see what the eigenfunctions are doing, they don't converge quite in L infinity because, well, they're taking 0 values pretty much all over the place. You can make this convergence in L2. You can make this convergence, how do you call it? You can make this convergence if you add a corrector. You can make it good enough so that, like you can use it for Pain's conjecture. And that's essentially what Hofmann, Ostenhoff, and Najrishvili did. So let's start by looking at the Schrödinger version of Pain's conjecture. It would tell us that if I have a continuous potential, then the second Schrödinger eigenfunction never crosses the positive, the region with positive potential. This one turns out to be false. Not only turns out to be false, it turns out to be very easy to disprove. Anything that you build, like for example, I don't know, a little double well. This was the first simulation that I tried. I put like some random potentials on the computer. First eigenfunction looks like this. Second one looks like this. You don't even have to try so hard. So morally, if you believe that the potential version and the non-potential version are equivalent, you spend half an hour scratching paper on the potential version, and you get a lot more insight than you would have gotten from the original one straight away. Now, I'm cheating a lot here. The microscopic hole situation that I talked about only works in dimension 2 and higher. If I pick a one-dimensional interval and I start cutting it, I lose everything at once. So this doesn't work. But what can I do? I can go to polar coordinates and I can build a radial version of this example. And the situation is exactly the same. I got the same example. You do it in polar coordinates. You use the polar coordinate version of the Schrödinger operator. Looks like that. I don't know if you probably see it. The red one doesn't cross the spike. You can plot it in polar coordinates. That means that we're using a potential like this on a circle. And at the bottom, you see in black the nodal line, and in orange the region where the potential is positive. As we see from the polar coordinate plot, they do not cross. Now, once I'm here, I have found the counterexample of the original problem as well, because I can simulate my Schrödinger counterexample by the microscopic, the microneedling strange term problems. So once I've managed to find an equivalence between the weighted and the unweighted problems, I can, if I want to build counterexamples, if I want to understand worst case scenarios and things like that, I look at the more general problem and I solve that one. Now, this is the classical result. Just for the sake of completeness, I want to say that this is not state of the art, and there was for a while a whole competition to see how many holes could you use. Because here I'm using infinitely many holes. This, if you really, really tried, you could try to make it effective, but no one wants a counterexample with 20,000 holes. So people instead tried first, historically, computational examples. So Joel, Daphne, and Javi and Kimberly tried to find counterexamples. They did a bunch of straight up numerics with interval arithmetic, proven estimate, and they found a counterexample with 6 holes. One of the things that really inspired me from this paper that's going to show up later is that they do really explore. They pick a space of configurations that they think is appropriate, and they really did a grid search over that space, and they found this. What turned out to happen, though, is that there are counterexamples with 1 hole. They're just very different from this. But I want to show you because it's like a proof by picture. And this is a paper from last year. So this is not a counterexample with 1 hole. It's a rectangle. If a rectangle was a counterexample, we would know probably. And the nodal lines in the middle going top to bottom. So, I have a problem here. I have a problem here. I want to get rid of these problems. How do I do it? Well, I could try to sort of push them to infinity. I make a very long line. And somehow, the problem's further and further away. Now that it's further and further away, I could try to bend this a little bit. And this works. So you can find counterexamples to Pain's conjecture with a single hole by this sort of argument where you glue a very, very, very small, very thin passage from one end of the nodal line to the other end of the nodal line. And you just glue the problems together. On the situation for simply connected sets, we have it's a bit more complicated. But this is Dirichlet. What can we say about Neumann? And this is what most of my talk wanted to be about. The idea from now on is like apply variations of this take to other scenarios, to Neumann scenarios. So let's talk about the hotspots conjecture. What does the hotspots conjecture tell me? So I'm going to switch from the Dirichlet world to the Neumann world. I'm going to be looking at temperature evolution in an insulated material. So here on the left, I have some potato, some material which is like, I'm going to assume like isotropic, sort of uniform, but has non-uniform temperature distribution. And the question I'm going to ask is, how does the temperature in this material evolve? And we can simulate it. And to no one's surprise, the temperature goes to the average temperature. Now, we like to say like non-obvious things. We want to go beyond that. So maybe instead of just saying the obvious, we can ask ourselves, how does the temperature converge to the equilibrium temperature? How would I even measure that? Well, instead of plotting the temperature over time, I could plot to you the temperature fluctuations over time. So I get the temperature, I subtract the average, and I renormalize to get an object that has sort of size 1. And I can, just get the same simulation as before, but now plot the temperature fluctuations. This is a, PDE with like more complicated dynamics and so on. But you can run a bunch of simulations of this sort on different domains, and you always see the same thing. Somehow, your domain has like a longest or like, least accessible direction where the heat is going to have the most trouble diffusing. And for long times, what's going to dominate is this longest direction. And not only that, like you try to formalize this for complicated domains, like defining even longest direction may be hard and so on. But there's one very weak claim that you could try to make, which is, well, I don't even know which is the worst direction. But if I claim that like locally there is a worst direction of some sort in any way, the largest temperature fluctuations for a long time should be at the boundary, because I just should, I should follow this like locally worst direction. And maybe this is true. Let's try to formalize all of these. Let's try to see what happens in like this long time asymptotics. So the situation is very similar to before. I pick my initial data. I can always express my initial data as a linear combination of eigenfunctions. Now, what do I know about the eigenfunctions? Some easy things. First eigenfunction is constant. We're in the Neumann situation, so Laplace of 1 is equal to 0. Normal derivative for any derivative of the function 1 is 0. And already by orthogonality, I see that all of the other eigenfunctions must have mean 0. This also lets me solve for all times for free. I have an infinite series. I know how to solve for each eigenfunction because the PDE becomes an ODE. So I can just solve like this. This already, solves the easiest question for me, which is that the temperature must converge to the average temperature. I start with a linear combination of things. The first one's the average temperature because the rest have average 0. All of the other ones go to 0. So asymptotically, I converge to the average temperature. Well, we've done half of the questions we had. Maybe the other half is comparable. You can do something similar. You can see that the asymptotic fluctuations converge to the first eigenfunction that has a non-zero coefficient. So you have, when I subtract the average, the first term is going to 0. And I have a series of terms exponentially going to the bottom, exponentially going to 0. So what's going to happen for large times? Well, the lowest one that's not already 0, and that's going to 0 this lowest, is the one that's going to eventually win. So eventually, these fluctuations converge to the first non-zero eigenfunction. OK, so the first non-zero eigenfunction is the first eigenfunction with non-zero coefficient is the limiting behavior. If I somehow believed, if I was very brave and I was like, for every initial data, the limiting asymptotic fluctuations have the maximum at the boundary. Well, this turns out to be equivalent to asking whether it's true that for every domain and for every k, the maximum and minimum of the first eigenfunction is at the boundary. This turns out to be slightly too strong. Again, our enemy is the circle. We look at the third one, it's radially symmetric. So it can't be the case that the maximum and the minimum are both at the boundary because it's radially symmetric, so it can only take one value at the boundary. So we have to tone down our expectations a little bit. What happens generically? What happens for typical initial conditions? Maybe there's like some probability zero bad cases, but generically I expect all of these coefficients to be non-zero. So maybe the conjecture that I should be asking is the maximum and the minimum of the first eigenfunction attained at the boundary? And that was Rau's hotspots conjecture. That for the first one, which is the one that we see for generic initial data, the maximum and the minimum are at the boundary. Now, what makes the first one special? The first one special because it minimizes the Dirichlet energy. If I look at the Laplace operator and I look at it in its weak form, it becomes the Dirichlet energy. And when I write the Rayleigh quotient, I'm trying to minimize this Rayleigh quotient over all mean zero functions. So it's this sort of challenge where you're trying to build a function that's as constant as possible, while it's a function that's as constant as possible and as big as possible. And somehow it's going to be trying to exploit the shape of your domain to become as big as possible while moving as little as possible. So it makes sense to think that it's going to try to pick the longest path it can take inside of your domain to grow as low as possible. And it's never efficient to go like up and then down again, because you would be spending like Dirichlet energy and you're trying to optimize for it. So that's it's sort of the good expectation. So what do we know? What have we known historically? So we know that the conjecture is true over the reals. This is good. The whole problem is translation and dilation invariant. It only makes sense for bounded sets, so we have exactly to check one thing, which is the interval 0, 1. We check the eigenfunctions, the cosine, we win. What do we know in R2? In R2, we know slightly less. We know it for triangles, and this is hard. Like triangles are surprisingly hard, but we know how to prove it for triangles. Now we have even a couple proofs of the conjecture for triangles. We know it for convex sets as long as they have one axis of symmetry. The way we exploit these axes of symmetry, I mean, morally the whole point, what we've been talking all about is like the longest direction and so on. The proofs go by guessing the longest direction and going on there. So if you have one axis of symmetry, you can guess that the longest direction is going to be either that or the orthogonal, and you can exploit that. We also know it for domains that are called Lip domains, which are in a certain sense, long. So they're between the graphs of two one-Lipschitz functions, which already forces them to be longer than taller, because they're between the graphs of two functions that have slope plus at most 1. So they have to be long in a certain sense. And again, the idea is the same. Since it's long, I know which is the longest direction. I'm going to prove that there is monotonicity in the longest direction, and then the maximum is at the boundary. Now, and this should be a D. In RD, we know it well for cylinders and product sets. This is sort of cheating because eigenfunctions tensorize. And we know it for a certain generalization of Lip domains, which are instead of between one Lip functions, between one Lip graphs with certain algebraic structures that let the proof go through. But it's extremely hard to understand what's going on in high dimensions because we barely understand what's going on in dimension 2. So in the middle of all of this general lack of understanding, came a question where it's like a gauge your optimism kind of question, where you have to decide how much do you believe in this physical intuition. Seems very reasonable at the beginning, so maybe you could believe that the conjecture is true for any smooth enough domain, or any domain. And this was the original one. And then Burzi and Werner came with this counterexample, and they showed that it's false. How does this counterexample work? How should I model this counterexample in my head? Well, it's a counterexample where, what do I want to say? It's a counterexample which is trying to get the third eigenfunction from before. Remember, we saw for the circle that the first eigenfunction satisfied the hotspots property, but the third one did not satisfy the hotspots property. So what this counterexample is trying to do is it's trying to swap to get the third radial eigenfunction and bring it below the first one. How is it doing that? Well, I'm trying to minimize the Dirichlet energy. So if I remove all of these areas, I'm building like very big like radial disconnection so that it's actually energetically very favorable to be sort of constant on the top and sort of constant on the bottom. And this is sort of like the punchline all along on this part, which is you have whatever eigenfunction has the properties you want, and you want to move it to be the bottom one. And once you do that, you find the counterexample. Now, maybe this is about topology. Well, it turns out no. It turns out that at least in dimension 3 and higher, you can, again, perform little surgery operations to save your topology to find counterexamples that are homeomorphic to a ball. Basically, in 1D, if I try to like cut this to make it homeomorphic to a ball, it's not going to work because suddenly my domains completely change. But if I have like a 3-dimensional version of this and I cut like a microscopic perforation to like make it homeomorphic to a ball, the Laplacian's never going to see that. Therefore, I'm going to get counterexamples. These are the same ideas that James Kennedy used at the time to find counterexamples for the previous conjecture without any topology. 2D is different because I can't cut things in 2D because we have complex analysis. So maybe it's true. And then there's like all of these way stronger situations like convexity and so on that I'm going to talk about later. So before we go to like restricting the domain, let's keep in like general domains, and we ask ourselves, well, the conjecture is false. What can I save? Well, Steinerberger proposed to us to look at the hotspots ratio. Instead of like trying to like teach the conjecture, quantify how false the conjecture is. So you divide the maximum of the eigenfunction inside by the maximum of the eigenfunction of the value. And you ask yourself, what's the value of this quantity? Now, first thing we know is that it's at least 1. Because we have counterexamples. If we didn't have the counterexamples, this would be 1. So is this bigger than 1? And what Steinerberger already proved in his original paper is that the conjecture is false, but it's not embarrassingly false. So he proved to us that the constant is at most 60. And this was further improved about a year later by Mariano Panzo and Wang, who basically got Steinerberger's proof, tried to like fix the constants a bit better, and they found a really nice asymptotic value. Again, all of these are upper bounds, but there's like this really mysterious upper bound, which is square root of phi that comes out of the proof. It comes like really cleanly. And if you take the maximum of what they find, it's probably 5.5. And this is where Mitchell Taylor and Alex Hu came into the question. And we asked ourselves, like, OK, there's this team of people fighting from the top. Can we try to find interesting counterexamples from the bottom? And try to evaluate like quantitatively, like what's our understanding of the conjecture. And we tried. And it worked very well. We ended up finding the exact value of the constant in every dimension. So it turns out that there's this PDE that you can solve, which is the Laplace equation with like radial symmetry on a ball, which is no longer a Neumann eigenfunction. Like this function has no reason to have anything to do with Neumann eigenfunctions. But it's an eigenfunction with the Neumann eigenvalue, just one at the boundary. And it turns out that the solution to this PDE in every dimension dominates any quantity you may care about regarding the hotspots conjecture. In particular, its value at 0, which is the maximum, is the hotspots ratio. So this is the exact value of the hotspots ratio. What's funny is that Mariano Panzo and Wang had already guessed the square root of phi. Like they didn't have like any hint from like lower bounds or anything, but it turns out that their asymptotics were sharp. Now, going back to the idea from before, these are the 3 eigenfunctions that we have. And we want to play a trick similar to the trick that we played, that Hoffman, Ostenhoff, and Nadirashvili played in Payne's conjecture. But we want to play a trick now that gets our 3rd eigenfunction and moves it all the way down here. But we want to do it in a sharp way. And when we do it in a sharp way, we create this sort of like ghost eigenfunction, which is solving a completely different problem. And it turns out to be the one on top. So we create like a new effective operator that looks like the ball, the domain looks like the ball and so on, but it adds a new weird eigenfunction, which is not even orthogonal to the other ones. Basically everything has broken at this point. And it has to satisfy that equation above, and again, it has to have an eigenvalue that's below the first one, and that explains why we get the same eigenvalue. And okay, the proof has two things. One direction, it's like standard tools. The other direction is going to be build an example. So let me start with the standard tools. I just have to introduce one tool. So we have this thing called symmetric decreasing rearrangements, which is very useful whenever you want to optimize and find sharp constants, which is this idea where you have a function which has all of its mass, like, maybe it's big here, and so on, and you squash it all to the center. So you build a new function where the superlevel sets, the law have the same measure, but it's radially symmetric and decreasing. So it's like a centrally squashed version of the original function. And there's this really cute theorem by Talenti, both really cute and honestly like extremely like powerful, which tells you that if you're trying to solve some sort of Laplace equation and you want to optimize, you should make the right-hand side be centrally symmetric. What it tells you is that if you pick a solution and you rearrange it, you're going to get something that's smaller than if you had first rearranged the right-hand side and then solved. If you rearrange the right-hand side, you're going to get something that's like radially symmetric and decreasing. So the solution is also going to be radially symmetric and decreasing. And this has, like 25 generalizations, works for eigenfunctions if you use it in the right way, works when you have domains, as long as you also rearrange the domain, and so on. And that's the punchline. This plus classical inequalities. Yeah, exactly. So it works. It's extremely robust. So, I can even give you a complete proof. It's a very simple upper bound proof. So I have my original eigenfunction, the one that satisfies the Laplace equation. It satisfies Neumann boundary conditions, but I've forgotten about it. I'm not even going to use that. And I've normalized it so that the maximum at the boundary is 1. At this point, if I give you a PDE like this, there's exactly one thing that you can do, which is maximum principle. The only thing you have is control at the boundary. So you know that you can control this by something that's slightly bigger, where you've changed the boundary value data to be 1. So if you find bounds for this one, you will find bounds for the previous one. Now, I have a Dirichlet problem with boundary data, it's an eigenvalue problem, but it doesn't matter that much. And it's in a domain that I don't like. The target theorem was about something happening in the ball. Well, we have Talenti. Talenti tells me that if I go to the ball, I'm only going to get something bigger. So I apply Talenti, and I go to the ball. Now I have one last thing that annoys me. This is not the eigenvalue, the Neumann eigenvalue of the ball. This is the one of omega. But we have an inequality, which is Jaeger-Weinberger. Yeah. No, but it turns out that you can, for example, apply Talenti to eta minus 1. And then, yeah, you substitute eta for eta minus 1, and then you apply Talenti to that, and it works. And also, I'm cheating a bit. I don't have 0 at the boundary. I have f also in the right-hand side. So you have to, it's, if you, like, the way that we actually do it in the paper is we apply Talenti to eta minus 1, and not only to eta minus 1, but to the fixed point iterates that you use to compute the eigenfunction. So like how do you compute an eigenfunction? You do like fixed point iterates to like Laplace to the minus 1, and we actually see that every fixed point iterate is bigger. The point is that Talenti it turns out that Talenti, as long as you're not doing something criminally wrong, you can always like squeeze Talenti into there by changing the argument a little bit. I agree this is not literal Talenti. It requires like half a page or 1 page of work, but yes, but you can turn this into Talenti. And now, once you're here, you just realize that you got the wrong eigenvalue. But we have Jaeger-Weinberger, which tells us that this is going to be as big as possible for the ball. And again, you have a monotonicity property that if lambda is bigger, this grows. In this case, you have exact solutions, so you can prove a nonsense monotonicity property, or you can look at the solutions and see that it grows. And in any case, you apply Jaeger-Weinberger, and you get the upper bound. All of these, Neumann we have never used, yet this is sharp. Like the fact that you can find a proof like this is not surprising. Well, at least what I find surprising is that a proof like this actually gives the sharp result for the hotspots conjecture. And yeah, I've used Neumann for Jäger-Weinberger in the sense that I've used that it's the eigenvalue, but this would also be true for any other function that satisfies the eigenfunction equation with the Neumann eigenvalue, but no boundary condition. It's like I've used the boundary condition to get the eigenvalue, but from then on you could pick any function, pick a Bessel function that has the same how do you call it? A Bessel function that satisfies the equation and has nothing to do with your domain. The proof will still apply. That's sort of. But I agree. Yeah, we need to use that the eigenvalue is the right one. It also works for other eigenfunctions. So it will also give you like a hotspots ratio for the second eigenfunction. Yep. No, but at this point, when I've done like this step over here, I've lost like when I've applied the maximum principle and I have one at the boundary, I've completely disregarded the change of sign. Like I've built yeah, exactly. The problem should be very complicated, but at the first step, I've destroyed all of the structure, which should be extremely lossy. Yeah, I completely agree. If you look at the original problem, there's a lot of subtle things that we were all convinced were very important, and it turns out that you just throw them away by maximum principle. Now, maybe at this point you have belief issues, which is completely understandable. So I'm going to give you a sketch of the proof of the lower bound. So what we did when we were proving this is we went back to the Burzi-Werner counterexample, which before had like 4 little gaps. Now it has 5. Before it was longer. There's like a 3-parameter family of Burzi-Werner type counterexamples, or 4-parameter depending on how you count. And you can try to run optimization over this family. And this is what we did, and we did it in a very brute force manner. You can build a bunch of them. You can build a lot more of them. And you can computationally search for the best one. Now, first thing you realize is that there's a partition into 2 regions, depending mostly on the connectivity between the 2 parts, which is, do I pick the radial eigenfunction or do I pick the non-radial one? So this is like a crossing of is the radially symmetric the first one or is it not? And the eigenvalues have to cross each other. It's very robust to perturbation, and you have to cut your possible domain into pieces. One piece which is completely hopeless, and one piece where you're doing the constraint optimization that you're trying to do, and you run it, and you find that this is the worst, or the worst that you can fit in a computer. And then you look at the picture and you pretty much understand what's going on. The counterexamples have a lot of holes. They're going to the boundary, and yeah, well, you have a bunch of holes going to the boundary. And from a mathematician point of view, this is good news, because suddenly I can hope to prove things. If the extremizer had 27 holes, I wouldn't know what to do. But if it has infinitely many, maybe I can squint my eyes and the holes are no longer there, and we're exactly in the Hoffman-Osten-Nadirashvili type of results again. And not only that, we realize that this idea at some point we learned was also proposed by David Jerison and Nikolai Nadirashvili in their paper on complex sets. They say there's this counterexample by Werner, but you can do it a lot easier. You just you build what's called a Neumann sieve, which is precisely this. And what do we get in the limit? Let's say you managed to take this limit effectively. Even if I don't know how I'm going to make this limit effective, I'm going to get something that should have eigenvalue below the first non-trivial eigenvalue of the ball, because otherwise it would not be below the trivial one. And it has to be radially symmetric. So it has to satisfy this equation. The maximum will be somewhere inside. The maximum at the boundary will be somewhere right at the edge of the sieve. And I can normalize it so that at the edge of the sieve, it takes maximum value 1. So I should get something like this, which is exactly the equation that you got before. And you can make this true. You can make like a microscopic, like the amount of holes microscopic and so on. And you can get that the first eigenfunctions will go to the minimizer of a problem where you have the usual Dirichlet energy plus a jump term that comes from the sieve. This is something that had been studied historically. Like I'm putting the statements from our paper, but I don't want to claim like any sort of like ownership or precedent because this has been extremely studied by people in this sort of like homogenization theory. And you apply this kind of results, you get an effective problem, and now you can solve this problem exactly. Because it's again a very beautiful radially symmetric problem. You go to polar coordinates, you solve and you win. Maybe too fast. Yeah.
Distance you go to the boundary versus the size of the holes?
So we do, I don't know, we do the limit by steps. Like we take one limit after the other to make the proof. Yeah. So the way we do it first we stay at a fixed distance from the boundary. Then we build a sieve over there. Then we get an effective problem that looks like this. And now the holes have completely disappeared from our mind. And then we do optimization over the effective problem. So it's like what we did at the first step, like you build the effective problem and you optimize over the effective problem, and then by that there would be a sequence of set and so on, but you've lost control at this point. But yeah. Oh, we have stability results. They're great. But they're criminal. So what we can prove is that we know that the ball is not an extremizer for the hotspots constant. I don't know if this is a question you have, but like we know that.
Change the boundary from a circle to an ellipse.
Yeah, exactly. So what we can show is that if you want to find like almost any extremizing sequence, we'll have to converge to a circle, to a circle with holes. This we have a theorem that says that, and there's like this quantity called the Frenkel asymmetry, which counts the maximum distance between your domain and a circle. And we also have sharp estimates that tell you if you have something that is very close to being a counterexample, then its distance from a circle, its Frenkel asymmetry, has to be very small. And we can quantify that. Like we have like sharp, it's the typical like square root type. The distance to a circle has to be like the square root of the error, the typical stability results that one expects in this situation. So yeah, we have sharp stability results. Morally, what's happening if you go to our original proof, you need to have stability for each of the inequalities that I proved. And you have Gero-Weinberger, we pick Gero-Weinberger, stability for that basically gives you everything. So we know that all the counterexamples have to look very close to this, and we can quantify by how much.
So all the counterexamples are close, or only the extremizers, in the sense that if you
all sharp counterexamples.
if you build a Neumann sieve like this for any starting domain, do you expect to get your hotspot ratio above 1, or?
My bet is that for every domain you can build a sieve, because again, like here I'm just showing you like the most specific situation, but you can how do you call it? You can also like perforate a lot of areas of your domain. You can be as nasty as you want with the perforations, and then you can simulate like very complicated variable coefficient PDEs, and then you can use this very complicated PDEs to do whatever you want. The running idea is always the same. None of this should be true for variable coefficient. You can always simulate variable coefficient. Yeah. Okay, so in the last few minutes, I wanted to talk a bit about what happens with less strange domains. Like, can I reproduce this strategy for domains that are reasonable? Like the punchline of everything I've given you so far is add infinitely many holes, or something that's not going to happen maybe for normal domains. And going back to where we were, this was our optimism level. Well, it turns out that for convex domains in RD, the conjecture is also false. And that's what I'm going to talk about a bit. Now, the question is, first, how do I even build in the convex world? Like, variable coefficient things. What do I play with? I cannot perforate. I cannot do anything. So what's going to be the substitute? So pick a bounded convex. So this is the hotspot conjecture. How do I upgrade it to something variable coefficients that's more likely to be false? Well, you can at least add a potential, it turns out. You can pick a convex potential, and then you can instead look at the Langevin operator associated to that extra potential. And how are we going to do that? Well, we can't add holes, but we can add dimensions. So you can add a lot of like extra microscopic dimensions that play the role of the holes. One direction is easy. You set v equals to 0. In the other one, what you do is you pick your potential and you add a bunch of extra dimensions. And you use like the thickness of these extra dimensions to model an effective potential. What's the key insight? How do these sets work? So what you do, an n and d should be the same. There's an n, this d should be an n, and this d should be an n, sorry. So what I do is I add n more dimensions to my domain, and I use these n dimensions to build something that has a thickness that's proportional to this 1 minus v over n. Now, where does the 1 minus v over n come from? Like, what's the story? So the radius of this is 1 minus v over n. And then this tells me that the volume of the slices is like e to the minus v. What's the whole point? This e to the minus v is the measure that's always associated to these types of operators. What do I mean? Let me give you like a concrete statement. So it turns out that in the same way that the Laplacian is related to the Dirichlet energy, these LV operators are related to the Dirichlet energy with a weight e to the minus v, in the sense that these operators are self-adjoint with respect to e to the minus v, and they represent the Dirichlet energy in e to the minus v. Now, once I know this, together with the fact that each slice is measuring like e to the minus v proportional volume, I can build a little map between my original like barrel-like set and a proper cylinder. I mean, there's only one reasonable map that one can build from one side to the other, which is the one where you repair the radius to make it 1 or epsilon. This map has two properties. First one, the differential of this map in terms of operator norm is almost the identity, because it's like a 1 over n perturbation. What this tells me is that when I pass functions from one side to another, the gradients are only going to change by 1 over n. And also this map is almost measure preserving. The reason is that the Jacobian of this map is like the determinant, which has like this n contributions, 1 per dimension. So it's going to be 1 minus v of x over n. Again, this n should be outside. To the minus n, which is e to the v of x. And these two cancel out exactly. So you have a map that's almost an isometry and almost measure preserving, which turns out to be enough to say that anything like Dirichlet energy related will be essentially the same, eigenfunctions will go, and so on. And here I have a cylinder. Cylinders we understand. And I thought I was going to have time to explain to you how to disprove the conjecture. But just let me tell you that at this point, what we're trying to do is finding a counterexample to this type of object, minus Laplace plus flat degree dot grad in very high dimension. And what we do is we play yet another trick, which is we look at a potential that is in radial coordinates. And you show that the first eigenfunction is going to be radial and so on, so that you can plot things. And it's kind of magical, because you want to show that the first eigenfunction of a cylinder like that has the maximum and the minimum and the middle. And when you change coordinates, now you want to show that it has the maximum and the minimum at the boundary, which is r equals to 0. But it's the right part of the boundary. So you've shifted a very hard problem, which is putting it in the middle, to a way easier problem, which is shifting it to where you want it. And the real advantage of working with the more general problem with grad v grad is that this change of variables, when you change in polar coordinates, the Laplacian stops being the Laplacian, and it gains another term, which is a grad v, like a 1 over r times partial r. But this term you can just reabsorb into the potential. So when you go to polar coordinates in these type of problems, you haven't really changed the type of problem in the same way that you would have changed the type of problem if you just were working with the Laplacian. So you stay like stable in the class, and now you want to find counterexamples over here. And it's a careful like tuning exercise to build counterexamples. And we can simulate them, we can make proof by picture, but I think I'm about out of time, so I'm not gonna, gonna skip very fast. They sort of, you build them by hand. It's like very carefully crafted, like piecewise linear functions that end up working. And if anyone has questions, I'm super happy. Like I'm gonna be here for the next 2 weeks. If anyone has questions, I'm super happy to talk about how this works. But the last thing I wanted to say is a bit of like, what can we do with this? So my claim is that there's this table where you can go from Neumann, Dirichlet, general domains and convex domains, and there's a whole corner that's underexplored. And there's a bunch of conjectures that fit here. So it's sort of, the reason also I presented Pain's conjecture is because I believe that there's fun stuff here where one can just by analogy complete the square and hopefully prove interesting stuff about high dimensional eigenfunctions in the Dirichlet regime. Just essentially by interpolating in the table and hoping for the best. So yeah, thank you very much.
Thank you very much. Questions, please. Sean?
So, in terms of failing the hotspots conjecture, do you expect that let's say a generic domain for whichever definition of generic you would like, should it satisfy or not satisfy?
A lot of people have asked me that, and I have no idea. Like what I can tell you is that failing is an open condition, which is like telling you nothing, but I don't know what's like the reasonable class of, yeah. I wouldn't be surprised. Like I think this genericity can be a little bit easier to formalize in like the log concave in the potential setting, where at least there I know how to make a statement, or I think I know, but I have no idea of the truth value of the statement.
Is it the case also that not failing the hotspot conjecture is also an open condition, like that both are?
So it depends. Like right at the bound, there's certain boundary cases where you have to be very careful if you have multiplicity of eigenfunctions. Like, if you can promise me that there's no multiplicity, then not failing is closed, where you would have like well, it depends on, like you could have like interior points that have equality with boundary points, like right before it appears. You have to be very careful then what happens when you have multiplicity of eigenfunctions. Other than that, and it's closed, it's not open. Yeah.
Any further questions?
Logistical questions. If you have some open questions, you can, on Friday we'll have
Yes.
session. So if you would like to maybe have half an hour to present this
Maybe,
square
yeah.
please let me know, and I'll be happy to hear the other people.
Yeah. It's a commercial break.
Commercial questions.
Could you clarify the last slide, Jerrison's Hessian conjecture?
This is one of my.
On the previous slide.
Yeah.
So this is one of my favorite ones, actually. And I'm going to write straight up the, how do you call it? The potential version, because it's the one I like, which says as following. So you pick any peak V convex. And let's say strongly convex to avoid like degeneracy. And then for any, I don't know, epsilon delta in 0, 1, there exists a constant where this constant is only going to depend on delta and d, such that for any xy in the set, It's the set where phi v S, set of S phi v of S bigger than delta times the maximum of phi v1. So any 2 points that are like not too far, like not at the tails of the eigenfunction. This eigenfunction is going to be a Schrodinger eigenfunction, so it's going to sort of look like a Gaussian. And then you pick points where it's big, like not too small. And then the claim is that the Hessian of the log of phi. So we know that minus log phi, where phi is phi 1v. We know that phi 1v is a log concave function, so this is the convex function. So evaluated at x. Evaluated at y. So if your potential was quadratic, then the first eigenfunction would be a Gaussian, and then this would be an equality. What the conjecture tells us is that this is sort of an equality. Like, that your eigenfunction, that there will be like some sort of like model Gaussian that your eigenfunction's modeled after. And the Hessian is really controlled by this model Gaussian in the bulk. Maybe as you go to the tails, we know that the constant has to degenerate. But as long as you stay in the bulk, there exists a model Hessian. Another way of saying this is that there exists a matrix that depends on the potential, such that instead of putting this, you have put so the Hessian at every point is controlled by the model Hessian, which would be the one that would sort of tell you what's the shape of your first eigenfunction. Something that's important to say, catching the shape is extremely non-trivial. So even a zero-order type of statement that lets you catch which should be M, so like not even a second-order statement, zero-order statement that tells you, well, M should be like this, in the sense, for example, that I give you a potential and you give me back a matrix, such that this matrix has the same like covariance and shape structure as the original one. That's already hard. This is known in dimension 2 and 3 if you work hard, but I think it's known in general. So it's already a hard problem. And then here you ask for a lot more. You ask for like precise second-order control.
Any further final questions? If not, let's thank the speaker very much.